Hello and welcome. My name's Dave Hicks. I'll be your chemistry teacher today, and we're going to talk about average atomic mass. Now here's our goals for the day. I want you to be able to understand the origins of what we mean by average atomic mass. What is it? Where do we find it? What things make it up? The origins. I want you to be able to identify which isotope is what we call the most abundant, meaning the most of, using this value of average atomic mass. And finally, you better get that calculator ready, because we're going to calculate some weighted averages to find the average atomic mass. Now, here's some things that you should know. You should know that every element has what we call isotopes. And isotopes are the same element, but they have a different mass. That's because they had a different number of neutrons, right? And the amount of these individual isotopes that's found in nature is really kind of set by nature. So anytime we get a sample of any particular element, we're going to find that it has generally the same amounts of each isotope that is part of that element. It's kind of set by nature. And then finally, the mass number of an isotope tells us the number of protons and neutrons. And maybe you've been taught that this mass number is a whole number, and it should be, because it's a number of protons and neutrons. So here comes the origins of this average atomic mass. What is it? Well, it's this unrounded number that we have on the periodic table right here. So you see, like, lithium is 6.9. What in the world, huh? Magnesium 24.3. Potassium 39.1. Titanium 47.9. These unrounded mass numbers on the periodic table are the average atomic masses for these elements. Now, they take into account all of the isotopes that are present. It's like the average mass, if you could just take all of the isotopes into account, weigh them all, divide by the number of isotopes, that would be its average mass. Now, we can't count all of the atoms that are part of a sample because, one, we can't see them, and two, they're just way too big. So we, as scientists, we figured out a way of counting and calculating this average atomic mass through what we call a weighted average. And this, we're going to use the mass of the individual isotopes and what fraction or what percentage of abundance that we find them in nature. And then we're going to work a formula to come up with those numbers that we see on the periodic table, the average atomic masses. All right. So, weighted average, how is it different? Well, whoops. The weighted average is different. If we take a normal average, let's say we had three things, and one of them has a value of 3, and another one has a value of 8, last one has a value of 5, and we average those three things together, then we would just take the 3 plus the 8 plus the 5 and add them together, divide by 3, and we would get 16 divided by 3, or about 5.3. Now, that's the way we normally do an average, right? How is a weighted average different? Well, for a weighted average now, instead of having one with 3, one with 8, one with 5, now we take into account how many of each of these we have in our sample. So like I've drawn a little sample over here. And in the sample, I have one of them that is a 3, and I have one of them that is a 5, and all of the red ones you see there are all 8s. So if this were true, then to take my average, I would take 3 plus 8 and 8 and 8 and 8 and 8, all the ones that were 8, right? Plus 5. and I'd add all those together. And when I add all these together, I would get 72. And now I have a sample of 10 of these here. So divide this by 10, and I get that the average for this group here, this sample, is 7.2. Now look here, the average is around 7.2. That makes sense to me because most of my sample has a number of 8, right? Has a value of 8. So you can see that it's moved the average from somewhere just sort of splitting it in the middle. It's moved the average to be closer to whatever value is what we call the most abundant value. I can either see the most abundant value if I could just count them, or I can do it in percentages. Hey, let's try this one more time here. Slide things around a little bit. There we go. So now this time, I'm going to have 80% of my values be 3. 10% are 8, and 10% are 5. So now that I have different values, if I add all these up, 3 plus 3 plus 3 plus 3, all of them, plus 8 plus 5. If I add all those together, I end up with 37. Again, I still have a total of 10, so I'll divide that by 10, and I get an average of this of 3.7. Again now, see, this is pretty close to 3, much closer than the other two examples, and that's because most of our values are 3. Okay, so this is the weighted average. It's weighted because I have more of one of the numbers than I have of the other numbers that I'm working with. Kind of in conclusion here, if we were to finish this off, what we've learned from this slide here is this, that the average atomic mass is going to be closest to the isotope of greatest abundance. The average will be closest to the one that there is the most of. That makes sense, I hope. So, let's kind of look at this in terms of a chemical element. So, you need to be able to go backwards with this idea too. So how about if the question is that we want you to know which isotope is the most abundant in nature? So if we know that there are two different isotopes of copper, copper 63 and copper 65, and I know on the periodic table that it has the average atomic mass of 63.546. So which of these two is the most abundant isotope? Well, this value seems to be closest to 63. That would make the copper 63 the most abundant. If it wasn't the most abundant, if they were equal, then our values would be out around 64, right? But in this case, there's more 63s than there are 65s. So our average ends up to be around 63, closer to 63 than 64 or 65. All right. Finally, the last thing I said we were going to do is we're going to get that calculator smoking, and we're going to figure out how to calculate an average atomic mass. So I got a formula for you. Here it is. This is kind of a simple way of doing it. If I take the average atomic mass, and I'm just going to take the percentage of one of my isotopes times its mass, and add that to the percentage of the other isotope times its mass. And if there are more than two isotopes, you just keep repeating this again and again and again. Now, because these are percents and not fractions, that's out of 100. So in the end, I'm taking 100 of them, so I got to divide it by 100, right? All right. So let's take a look at our first example with this. Our first example here is boron. Boron here has two isotopes. One isotope is this boron 10, and you can see its average atomic mass is 10.0129370, etc., etc. Well, let's just limit things to like maybe 3 significant digits today, huh? So let's say that the average mass is around 10.0. Now, why isn't it exactly 10.0? Well, protons and neutrons don't weigh exactly 1. So even though when we're counting the number of them, we count each one as a single digit, 1, but their actual masses themselves are not exactly 1. And maybe if you want to study a little bit more on that, you can go right ahead, but let's just accept the idea that we're going to have to be given what the atomic mass value is. We can also see over here that the abundance of boron 10 is 19.9, 19.9%. Okay? Boron 11 is a mass of 11.0. We're going to leave it there. And we have about 81% of boron 11. So let's take these numbers. I got them right there. Let's take those numbers and plug them into our formula here. So we'll start out, I don't know, let's start out with boron 10. You could start out with either one, doesn't really matter. And I know that 19.9% of this is boron 10. And then I'm going to multiply it by its mass. And the mass, we said we're going to round off to 3 significant digits. So that'd be 10.0. Okay, done with boron 10. Now let's do boron 11. Boron 11 said it has an abundance of 80.1. And then I'm going to take this and multiply it by its mass, which we're going to round off to 11.0. There aren't any more, so I'll stop right there. Divide this whole thing by 100, because we're doing percentages out of 100, so I got to divide by 100. And when I crunch this whole thing out, the average atomic mass for boron comes out to be about 10.8. Go ahead, look it up. That's about what it is. Now, that's not a big surprise to me, because I see here that 80% of the isotopes of boron are boron 11. And notice that my average came out closest to 10.8. It's closest to 11, right? So that makes sense to me. All right. Hey, I did an example. How about you do an example? So let me pull up another example here. How about gallium here? So there's our average atomic masses for gallium. Again, let's round those off to just 3 sig figs. So we'll get 68.9 and 70.9. Gallium 69, 71. Again, not exactly 69 and 71, right? That's because of these masses are not exactly 1. And then over here, our natural abundances, again, let's round these off to just 3 sig figs too. So 60.1 and then 39.9. All right, I'm going to give you a couple minutes to go ahead and try to work this one out. And then I'll come right back after you hit the play button again, and I'll show you how I do it. All right, how did you do, huh? I bet you did great. Okay, so here's what I'm going to do. I'm going to take that percentage, 60.1, times its mass, the 68.9, plus the other percentage, 39.9, times the mass of 71, which is 70.9, divide by 100. Whoops, getting a little messy there. And in the end, my answer came out to be 69.7. Again, this is much closer to the gallium that is 69, right? 69.7, it's closer to gallium 69 than it is to 71. And that's because 60% of it is gallium 69. So this is going to be an advanced section of this, and we're going to play around with something mathematically. If you're in an AP course or an honors chemistry course, then you'll probably have to do this somewhere in your course. So what we're going to do next, one last thing, where we actually find the percentage of the abundance based upon the average atomic mass and the knowledge of the two isotopes. I'm going to limit myself to 2 isotopes in this case, because trying with 3 or more might prove to be a little bit difficult and is usually outside the scope of what you're doing mathematically. So remember our formula here. Our formula is this. I'm going to change it just a little bit. Again, you guys are advanced. If I distribute this 100 out into these percentages, I could use the percentage as a fraction instead of using it as a percentage. That might make our math just a touch easier here for this. That's what I'm going to do. If that really confuses you, I'm sorry. But kind of work through it there and see what I'm doing. I'm going to assume that the masses of chlorine 35 and 37 are about 35 and 37. They're not exactly, but they're close. And so I know what the average atomic mass is, and that's 35.45. I'll substitute that in. And the percentage here that I have is what I'm looking for, right? So since it's something we're looking for, let's just call it X. We're used to things being called X. So I'm going to say X, and I'm going to go times the mass, and I said we'll call this mass approximately 37. I'm rounding off, which is going to cause a little problem a little later on, but not too much. And then over here, I'm going to say, well, I want to take the percentage of the other chlorine, which is going to be chlorine 35, and with that, I don't know what that is. I can't call it X because X is the percentage of chlorine 37. So what I'm going to do here is I am going to play a little trick, mathematical trick, and whenever I have a 2-part system, right, if I know the one part, a percentage or a fraction of the one part, then the other part is just going to be 100% minus that, right? Or 1 minus that, since I'm working in fractions. So I'm going to call this percentage 1 minus X. And then I'm going to multiply it by 37, which is the approximate mass of my chlorine 37. So there was the trick on how to do this for a 2-part system. I make one of them X. The other one, since it's a fraction, is going to be just 1 minus X, the whole thing minus whatever part was the part that we already assigned X to, right? That's what's going to be left over. Now, quickly solving this out, I'm going to get that this is 37X plus, got to distribute here, 37, whoops, I made an error here. This should be 35, right? Let me get 35. That's distributed then is also 35. All right, so 35 minus 35X. Now on both sides, I'm going to subtract this 35. I'm collecting up like terms. I got to do it from both sides. So what's left over here is going to be 0.45 is equal to, I got rid of that, so now I got 37X minus 35X, or 2X, right? X equal to 0.225, which is my fraction. In percentage, this 0.225 comes out to approximately 23%. 23% of what? Well, 23% of isotope 37. So this is 23% of chlorine 37. And how much is the 35 then? Well, let's just subtract it away from 100%. And if I do that, then I get that it's about 78% of chlorine 35. All right. Well, I hope this helps you out in your chemistry. And good luck with things. And the next time you find yourself in need of a little bit of chemistry knowledge, please tune in again. Thank you, and goodbye.